So welcome to our class. In this chapter, the sixth chapter, we talked about the architectural design. We said that we can design software architectures at two levels of abstraction. Architecture in the small and architecture in the large. With architecture in the small, we are concerned with the way that an individual program is decomposed into components, and in architecture in the large, we are concerned with the architecture of complex enterprise systems that include other systems, programs, and program components. And then we have talked about three advantages of explicitly designing and documenting software architecture. Do you remember three advantages of explicitly designing and documenting software architecture?
Laoshi, they are stakeholder communication, system analysis, and large-scale reuse.
Yeah, thank you very much, Kaya. And Saji had answered correctly also. Yeah, we have talked about these three advantages. These three advantages of explicitly designing and documenting software architecture: stakeholders, communication, system analysis, and large-scale reuse. Two ways to use an architectural model of a program.
Laoshi, the answer is as a way of facilitating discussion design, and also as a way of documenting design.
Yeah, perfect. Thank you very much. Yeah, and Kaya, thank you. Yeah, perfect. It's like this. As a way of facilitating discussion about the system design and as a way of documenting an architecture that has been designed. It's here. We have talked about here. Yeah. Two ways to use architectural model of a program as a way of facilitating discussion about the system design and as a way of documenting an architecture that has been designed. You see, for the first way is a high-level architectural view of a system is useful for communication with systems and project planning because it is not cluttered with detail. Stakeholders can relate to it and understand an abstract view of the system. They can then discuss the system as a whole without being confused by detail. So this one is about the system to be designed. So we can facilitate different stakeholders to communicate on it. And for the second one, as a way of documenting an architecture that has been designed, the aim here is to produce a complete system model that shows the different components in a system, their interfaces and their connections. Such a detailed structural description makes it easier to understand and evolve the system. It is about an architecture that has already been designed. Okay, this is this one. And then we have talked about for the architectural views, we have said there is a well-known 4+1 view model of software architecture. In this model, we say there should be 4 fundamental architectural views which are related using use cases or scenarios. And use cases and or scenarios, this part represents +1. However, the other four fundamental architectural views. What are the four fundamental What are the four fundamental architectural views? What are the four fundamental architectural views in the well-known 4+1 view model of a software architecture?
Laoshi, I have three: a logical view, a process view, and a development view. I don't know the fourth one.
The fourth one is a physical view.
Oh, okay. Thank you, Laoshi.
Here. Thank you very much, Kaya. But it's perfect. You see here, for a logical view, it shows the key abstraction in the system as objects or object classes. Normally, it should be possible to relate the system requirements to entities in this logical view. And for a process view, it's to show how at runtime the system is composed of interacting processes. This view, it is useful for making judgments about non-functional system characteristics, such as performance and availability. You see, at runtime we can associate it with the performance, responding time, etc. Then it is a development view. It shows how the software is decomposed for development. That means how to break the software into components that are implemented by a single developer or development team. This view is important or useful for software managers and programmers. The last one is a physical view. It's to show the system hardware and how software's components are distributed across the processors in the system. This view, it is useful for system engineers planning a system deployment, as we need to distribute the system hardware and the different components. Here are the four fundamental views. Then we need to relate. These four views are related using use cases or scenarios. That's +1. So this is the 4+1 view model of software architecture. It is a very well-known architecture. Then the last part of the class, the last part of our class in I think on Monday, we have talked about architectural patterns. We have introduced one pattern, and this. Can you tell me what does M represent, V, C represent?
Like you're asking the abbreviation of MVC?
Pardon? Abbreviation. And it's like MVC is abbreviated for.
Okay, like model, view, and controller.
Exactly. Thank you, Shibli.
Most welcome, ma'am. Thank you.
It's the model view controller pattern that we have introduced in the last class. This model view controller pattern is also a very well-known pattern. It is the basis of interaction management in many web-based systems. Here we have some figures to show. I think, here. Here is a tabular description of this pattern. When we want to describe a pattern with a tabular form like this, usually we give the description example when used advantage and disadvantage as these different aspects of the pattern. In the description and examples, usually we have some figures to illustrate these things. As here we have a figure to show the organization of the MVC pattern, model view controller. And This figure is a web application architecture using the MVC pattern. It is an example. Yeah. Okay, now we'll continue with other patterns. Yeah. The second pattern we'll see is the layered architecture. Layered architecture is used to model the interfacing of subsystems, and we need to organize the system into a set of layers through this layered architecture. Each of these layers provide a set of services. That means, here the system functionality is organized into separate layers, and each layer only relies on the facilities and services offered by the layer immediately beneath it. This architecture or this pattern supports the incremental development of subsystems in different layers. While layer interface changes, only the adjacent layer is affected. You see, with this layered approach, as describes here, it supports the incremental development of subsystems. And with this one, when a layer is developed, some of the services provided by that layer may be made available to users. So the architecture is also changeable and portable. Once the interface is unchanged, a layer can be replaced by another equivalent layer. Also, when layer interfaces change or new facilities are added to a layer, only the adjacent layer is affected. Also, we say, as we have the layered system localize machine dependency in inner layers, it is much easier to provide multi-platform implementations of an application system. Only the inner machine-dependent layers need be re-implemented to take account of the facilities of a different operating system or database. As we put the essential ones in the inner machine-dependent layers. Here, this figure or this table describes the layered architecture pattern in detail. Yeah, as we have said before, when we describe a pattern using a table like this, we need to give some aspects like description, examples when used, advantage, disadvantage for this pattern. You see, for the description, the layered architecture pattern organizes the system into layers with related functionality associated with each layer. A layer provides services to the layer above it. So the lowest level layers represent core services that are likely to be used throughout the system. Yeah, here we have also explained, we say each layer has its functionality, and also a layer provides services to the layer above it. So the lowest level layer, that means the inner layer, represent core services that are likely to be used throughout the system. It's like the operating system or database in the inner layer. And examples for this pattern, a layered model of a system for sharing copyright documents held in different libraries. Yeah, here we will see an example of this pattern later. And this pattern usually is used when building new facilities on top of existing systems. When the development is spread across several teams, with each team responsibility for a layer of functionality, when there is a requirement for multi-level security. You see, with the layered architecture, we can separate the tasks into different teams. Then we build new facilities on top of existing systems. We base on the inner layer, then we add some functionality on the top layers. The advantage of this pattern is to allow replacement of entire layers so long as the interface is maintained. Redundant facilities like authentication can be provided in each layer to increase the dependability of the system. The disadvantage of this pattern is that in practice, providing a clean separation between layers is often difficult, and a high-level layer may have to interact directly with lower-level layers, rather than through the layer immediately below it. Performance can be a problem because of multiple levels of interpretation of a service request as it is processed at each layer. Here, it means with layered architecture, normally we should separate different services into different layers. But here, sometimes it's difficult to separate functionalities into different layers very clearly. Also, when we want to communicate the top layers with the inner layers, we need to go through with the intermediate layers. It's not very convenient in some situations. Here, this figure is an example of a layered architecture with four layers. You see here we have 4 layers. The lowest layer here, it includes system support software. Typically, we have the database, operating systems support. The next layer, second layer, is the application layer. We include the components concerned with the application, functionality, and utility components that are used by other application components, like core business logic, application functionality, system utilities. And the third layer, it is concerned with user interface management and providing user authentication and authorization. The top layer, this layer, it provides user interface facilities. Surely here we have we say this is an example of 4 layers. In fact, the number of layers here, it is arbitrary. Like in this figure, any of these 4 layers, we can split it into 2 or more layers. Like here, user interface management, we may leave it as a separate layer directly. Now this figure is another example. It is about, this example is this example is how this layered application architecture pattern can be applied to a library system called LabSys system. In this one, this system allows controlled electronic access to copyright material from a group of university libraries. Here we have 5 layers in this architecture. The bottom layers are the individual databases in each library. Then, the second layer is the library index for these different databases in each library. The third layer includes distributed search, document retrieval, rights manager, accounting, these different functionalities. The fourth layer includes libraries, login, forms, and query manager, print manager. Then the top layer is the web browser interface. Yeah, as we have said before, here the number of layers, it is arbitrary. We may have 6 or 7 different numbers of layers for one system, because we may split each layer into 2 or more layers. Okay, here it's for the layered patterns, architecture pattern. Now we'll see another pattern. As we have seen before, the layered architecture and MVC patterns, both of them are examples of patterns where the view presented is the conceptual organization of a system. We have, till now, we haven't talked about some data between these, data between these components or these organizations. Now, we'll begin to talk about a different pattern. It's the repository pattern. Here, this pattern describes how a set of interacting components can share data. Subsystems must exchange data. This may be done in 2 ways. Shared data is held in a central database or repository and may be accessed by all subsystems. Or each subsystem maintains its own database and passes data explicitly to other subsystems. You see, here we talk about 2 ways to exchange data. Either we can share data in our central database or repository, and then all subsystems have access to these shared data. Either each subsystem can maintain its own database, and then we pass data to other subsystems. When large amounts of data are to be shared, the repository model of sharing is most commonly used, and this is an efficient data sharing mechanism. If we need to share large amounts of data, it will be much more convenient to keep the shared data in our repository or in our central database, then others can have access to this data. This tabular shows the repository pattern. We see in this example, in this pattern, all data in our system is managed in our central repository that is accessible to all system components. Components do not interact indirectly, only through the repository. That means all subsystems can have access to the repository and use the shared data directly. They don't need to interact between those subsystems or subprocessors. We have an example of this repository pattern. We'll see it later. It is an example of an integrated development environment where the components use a repository of system design information. Each software tool generates information which is then available for use by other tools. Want to use this repository pattern? We can use this pattern when we have a system in which large volumes of information are generated, and that has to be stored for a long time. We may also use it in data-driven systems where the inclusion of data in the repository triggers an action or tool. As we see here, in these situations, we may have a large amount of data to be shared, or we need to communicate with many data. That's why it's better to use this repository pattern in these situations. And the advantage of this pattern is that components can be independent. They do not need to know the existence of other components. Changes made by one component can be propagated to all components. All data can be managed consistently. Backup done at the same time as it is all in one place. Here, we mean that with the repository pattern, as we can get data, we can have the access to data in the central repository directly. We don't need to have the communication with other sub-processes. In this way, once a sub-process has modified the data, we can get the modified data directly. We don't need to communicate with other components to see if the data is changed or not. And the disadvantage of this pattern is that the repository is a single point of failure. So problems in the repository affect the whole system. It's like it is consistent with the advantage. As we have only one place to put the data, we put them in the repository. So once there is a problem there, the whole system is broken. So this may be inefficient in organizing all communication through the repository. Distributing the repository across several computers may be difficult. These are some disadvantages of this repository pattern. I will note your attendance at first, and then we'll see some examples of this repository pattern in detail. If you have some questions still here, don't hesitate. Okay, perhaps we'll continue. Here we had a tabular description of the repository pattern. As you see, this tabular has the similar form as the layered architecture. The tabular description for the layered architecture. We have the description example when used, advantage, disadvantage for this pattern. And as we have said, for description and example, we may have figures to illustrate these two aspects. Now we'll see a figure for the repository pattern as an example. You see here, it's a repository architecture for integrated development environment. Here, this figure, it is an illustration of a situation in which a repository might be used. As we see here in this diagram, an integrated development environment includes different tools to support the model-driven development. The repository in this case must be a version-controlled environment, and it keeps track of changes to software and allows rollback to earlier versions. You see here we have a repository, and this repository can keep track of changes of different versions to software. Here we have different components that may get access to this repository. We may have design translators, design analyzers, report generator, Python editor, Java editor, code generators, or UML editors. You see different tools can have the access to this repository. That's for the repository architecture. In fact, organizing tools around a repository is an efficient way to share large amounts of data, as we have said before. There is no need to transmit data explicitly from one component to another. However, components must operate around an agreed repository data model. Like here, we must operate around this repository. So normally there is a compromise between the specific needs of each tool, and it may be difficult or impossible to integrate new components if their data models do not fit the agreed schema. In practice, it may be difficult to distribute the repository over a number of machines. Although it is possible to distribute a logically centralized repository, there may be problems with data redundancy and inconsistency. As here in this figure, the example, this repository is passive and the control is the responsibility of the components using this repository. An alternative approach uses a black box model that triggers components when particular data become available. Yeah, perhaps this one. Yeah, this is appropriate when the form of the repository data is less well structured. Decisions about which tool to activate can only be made when the data has been analyzed. We'll see, perhaps we'll have opportunities to see these, different changes. Now, we'll see another pattern, which is client-server architecture. The repository pattern what we have seen before, it is concerned with the static structure of a system, and it doesn't show its runtime organization. However, in this example, client-server architecture, it illustrates a very commonly used runtime organization for distributed systems. You'll see this architecture in detail. It is a distributed system model to show how data and processing is distributed across a range of components. It can be implemented on a single computer. It is a system that follows the client-server pattern. Yeah, this client-server architecture or pattern, it is organized as a set of services and associated servers and the clients that access and use the services. Is like what is said here. How data and processing is distributed across a range of components. It can be for this pattern, we may have different components, but some are major components, like here, like a set of standalone servers which provide specific services such as printing, data management, etc. That means for this model, one of the major components is a set of servers that offer services to other components. Examples of this kind of servers can include print servers, like here what is said, printing services, file servers that offer file management services, like data management. We may also have compiler server, which may offer programming language compilation services, etc. Other components may be a set of clients which call on these services. That means we may have a set of clients that call on the services offered by servers. Normally, there will be several instances of a client program executing concurrently on different computers, as these clients need to get the services. Also, for this Python, we need a network which allows clients to access servers. Most client server systems are implemented as distributed systems, and they are connected using internet protocols. Usually we think client-server architecture as distributed system architectures, but the logical model of independent services running on separate servers can be implemented on a single computer, as what we have said before. Here, an important benefit is separation and independence. Services and servers can be changed without affecting other parts of the system. You see, separation and independence, it is very important for system architecture, because once we have these properties, separation and independence, we may change one part of the system without affecting other parts. And with this Python, clients have to know the names of the available servers and the services that they provide. However, servers do not need to know the identity of clients or how many clients are accessing their services. And so for clients, they need to get these services, so they need to know the name of the services. But for servers, what they do is to provide the services. They don't need to know which clients need it or how many clients are trying to get the services. They don't need to know. They just provide the service. It's okay. It's different from clients. Clients, they need to get the services, so they need to know the name of the server. Clients access the services provided by a server through remote procedure calls using a request reply protocol, such as the HTTP protocol used in www. It's our as we have seen before, it's a web browser. It may be a web browser interface. Essentially, a client makes a request to a server and waits until it receives a reply. This tabular describes the client-server Python in detail. As said here, in a client-server architecture, the functionality Yeah, the functionality of the system is organized into services, with each service delivered from a separate server. As we said, each server provides some services. Clients are users of these services and access servers to make use of them. Clients need to know the names of servers to get access or to receive these services. Here we have an example, the figure to illustrate an example of a film and video DVD library organized as a client-server system. This client-server pattern, it is used when data in a shared when data is shared in is a shared database has to be accessed from a range of locations. Yeah, it's like what we have said, the repository pattern. You see here we need to get access to the data, to share the data. And the difference here is if we are from a range of locations, it's like many clients want to have the access, want to get the services provided by the server. So we need to use this pattern, as servers can be replicated, may also be used when the load on the system is variable. The advantage of this pattern is that the principal advantage is that servers can be distributed across a network. Yeah, we can distribute these servers in our network, and general functionality like a printing services or compilation of a program, they can be available to all clients and does not need to be implemented by all servers, by all services. You see here, with this pattern, we may have some functionality which may be shared by all clients. And as we have said before, the reuse is a very essential way in system development or in system design. So with this client-server pattern, we may also reuse some functionality for similar systems. The disadvantage of this pattern is that each service is a single point of failure, so susceptible to denial of service attacks or server failure. Yeah, you see, even here, it's like the repository pattern. Performance may be unpredictable because it depends on the network as well as the system. Maybe management problems if servers are owned by different organizations. Yeah, you see, each coin has two sides. With the advantage, we may have some disadvantage with these properties. As we are dependent on the network, we may have some unpredictable capabilities. Okay, here, this figure is shows an example of system that is based on the client-server model. In this system, we see that it is a multi-user. That means we have different clients, web-based system for providing a film and photograph library. In this system, we have different servers who manage and display the different types of media. Video frames need to be, why we need different servers? we have some reasons. For example, for video frames, we need to transmit it quickly and in synchronous, but at relatively low resolution. They may be compressed in our store, so the video server can handle video compression and decompression in different formats. Still, pictures, like here, pictures, however, must be maintained at a high resolution, so it is appropriate to maintain them on a separate server. These, and here, the catalog, it must be able to deal with a variety of queries and provide links to the web information system that includes data about the film and video clips. And an e-commerce system that supports the sale of photographs, film, and video clips. You see, the client program is simply an integrated user interface constructed using a web browser to access to these different devices. So this one shows that the most important advantage of the client-server model is that it is a distributed architecture. Effective use can be made of network systems with many distributed processors. It is easy to add a new server and integrate it with the rest of the system, or to update servers transparently without affecting other parts of the system. You see, with this distributed architecture, like this one, client-server architecture, we have the property separation and independency. Yeah. As we say, these are some important properties of system architecture. Now, we'll see a final example of an architectural pattern. It is the pipe and filter pattern. Functional transformations process their inputs to produce outputs. That means it is a model of the runtime organization of a system where functional transformations process their inputs and produce outputs. So we have the data flows here, and the data flows from one to another and is transformed as it moves through the sequence. Each processing step is implemented as a transform. Input data flows through these transforms until converted to output. The transformations may execute sequentially or in parallel. The data can be processed by each transform item by item or in a single batch. So we see here we are also concerned by data. We are concerned by runtime organization. Yeah, here the name of this pattern, pipe and filter, they may be referenced to they come from the original Unix system, where it was possible to link processes using pipes. I think you have Linux this semester. With these pipes, they pass a text stream from one process to another, and systems that conform to this model can be implemented by combining Unix commands using pipes and the control facilities of the Unix shell. The term filter, it is used because a transformation filters out the data it can process from its input data stream. You see, the original of the name pipe and filter. Also, for this approach or this pattern, variants of this approach are very common. When transformations are sequential, this is a batch sequential model, which is extensively used in data processing systems. That means here, since computers were first used for automatic data processing, we have used some variants of this pattern, this approach. And when transformations are sequential with data processed in batches, this pipe and filter architecture model becomes a batch sequential model. Also a common architecture for data processing systems, like the billing system. The architecture of an embedded system may also be organized as a process pipeline, with each process executing concurrently. It's not really suitable for interactive systems, as interactive systems are difficult to write using the pipe and filter model because of the need for a stream of data to be processed. Although simple textual input and output can be modeled in this way, graphical user interfaces have a different or have more complex input-output formats and a control strategy that is based on events such as mouse clicks or menu selections. So it is difficult to translate this one into a form compatible with the pipelining model. That's why we say this pattern is not really suitable for interactive systems. Okay, here we have a figure to explain this. This tabular is to show a detailed description of the pipe and filter pattern. As we have seen multiple times in our tabular description like this, we have different aspects like description, example, when used, advantage and disadvantage. To describe this pattern, the processing of the data in a system is organized so that each processing component or filter is discrete and carries out one type of data transformation. The data flows as in a pipe from one component to another for processing. For the example, we have a figure to illustrate an example of a pipe and filter system used for processing invoices. Normally, this pattern is used in data processing applications, both batch and transaction-based, where inputs are processed in separate stages to generate related outputs. And the advantage of this pattern is that it is easy to understand and supports transformation reuse. Workflow style matches the structure of many business processes. Evolution by adding transformations is straightforward, can be implemented as either a sequential or concurrent system. This one we have explained the sequential and the concurrent system before. However, it has some disadvantages, like the format for data transfer has to be agreed upon between communicating transformations, and each transformation must parse its input and unparse its output to the agreed form. This increases system overhead and may mean that it is impossible to reuse functional transformations that use incompatible data structures. You see here, we have explained some disadvantages of the pipe and filter pattern. There are also, some of them are also related to the advantage. As said before, we have given an example here. It is an example of the pipe filter architecture. In this example, we see here this example used in a batch processing application. An organization has issued invoices to customers. During a period, payments that have been made are reconciled with the invoices. For those invoices that have been paid, a receipt is issued. And for those, so we have receipts here. And for those invoices that have not been paid within the allowed payment time, a reminder is issued. That's what this diagram or this figure illustrates for the pipe with the pipe and filter architecture. Here it's for this pattern. In total, we have explained these different patterns. I think it's better if you can digest these different patterns. Okay, now we'll have a